Welcome back once again to another YouTube live session, and tonight we're going to be talking about power series. Especially we're going to get it started with radius of convergence, the radius of convergence and interval of convergence, and then we're going to try and represent functions in terms of power series, because that's our main hopes in terms of what's going on there. So as always, I see we have some mentioning in the chat session already, so if you have any questions, please ask away, and that's what I'm here for. So without further ado, let's kind of get started with determining the radius and interval of convergence for the following power series. And we're going to do about, I think, like 7 or 8 of these, just to make sure we get the hang of it, because that's the big trick. And it's kind of working with all those pieces that we've done before in terms of all the tests. So when you take a look at this one, you have x over 5 raised to the k power. The summations from k equals 0 to infinity. If we want to find the radius of convergence, we're essentially looking for something where we can take an absolute value of this and put it less than some r value. Okay, and the key to kind of break this one on down is probably to use the root test. And so what would the root test look like? Well, if we use the root test, it says, hey, we can take the kth root of a sub k. Now why the root test? Well, because everything's raised to that k power right there. You might see n used. I'm trying to use some different letters every now and then just to try and make sure that we look at this. Now we need, in order for this thing to converge, we need the kth root of k of ak to be less than 1. And so that leads us to, oh, I should put absolute value right here, my apologies. And we have a limit as k approaches infinity. So I'm getting a little sloppy there. There we go. A little better. Okay, so the limit as k approaches infinity of the kth root of, and then a sub k is x over 5 raised to the k. And this will cancel out with that, and so what we're left with, and all this should be less than 1 as well. What happens? Well, we get limit as k approaches infinity of just the absolute value of x over 5. And that's less than 1. Notice this doesn't even involve a k anymore. That's good, right? That's what we want to have happen, hopefully. And so since that doesn't involve a k anymore, what we can break this down to is the absolute value of x over 5 is less than 1. Well, that means that the absolute value of x is less than 5. Now this is the radius of convergence. So we have a radius of convergence is given by this r equals 5. But what it doesn't, notice we had less than immediately. It doesn't tell us about these endpoints when it actually equals 1. Remember, it's inconclusive for our test when in a root test we have that this value that we're taking the kth root of this absolute value a sub k, if that equals 1, we don't know. And so that's what we have to check. And so first off, so here's what we'll check. What happens when the absolute value of x equals 5? Okay, well, first off, this is meaning what we're checking is negative 5 and 5, and so we have a big question mark, and I'll put the question mark over the equal symbol right there. So we have negative 5, and then we have another one for 5. Okay, so what we'll do is we'll plug those things in. So we'll plug those in for x, and we'll figure out if it does have this satisfied. So when, I'll plug this up here, when x equals negative 5, what happens? We get a sum k equals 0 to infinity of, it goes negative 5 over 5 to the k, which equals the summation k equals 0 to infinity of negative 1 to the k. And that goes essentially 1 plus negative 1 plus 1 plus negative 1, so on and so forth. So this thing, it actually diverges by the test for divergence. So what does that tell us? Well, that tells us that this is a big no-go. We don't want to include that equal to symbol on the -5. And when k equals 5, we're going to get something similar. You get the summation k equals 0 to infinity of 5 over 5 raised to the k. And if you notice, that's just 1 raised to the k. Well, 1 raised to any power is just 1, so this is sum k equals 0 to infinity of 1. So you're adding up 1 an infinite amount of times. That also diverges by test for divergence. So that means the 5 is not possible. That's a not equal as well. So at the end of the day, what we have is the interval of convergence. So the interval of convergence runs from -5. We don't want to include that to 5. We don't want to include that either. And so that's our final answer. So we have the radius being 5, and then since our x, we just had x between those two, so it goes -5 to 5, and we're done. Okay, and as I said, ask questions as much as needed to try and understand those. So that was one of the easier ones to get started, and then we'll kind of look at some others along the way. Well, if we take a look at this now, this one's very similar. We have everything raised to the kth power. We can use the root test once again. So we take a limit as k approaches infinity and now we'll have the kth root, so absolute value of a sub k. And you can even toss that on the outside, it won't make much of a difference. You have -1 to the k, x minus 7 to the k, and then 3 to the k. And the reason why the kth root would work again is since all these powers kind of match up. You can rewrite this. So notice this thing can become an easier way to write that. Oh, and by the way, this is, we're looking for less than 1. Sometimes I get in the habit when I'm actually doing it on my own, I just actually figure this out and I just remember at the end that it's less than 1. But just to make sure that we're reiterating that here, I'll try and write it on every line for you. So at the end of the day, what do we have? We have the limit as k approaches infinity of the kth root of this absolute value of negative, and then we have x minus 7, and then all over 3, and all that's raised to the kth power. I can move that to the outside. It isn't going to make a difference, because at the end of the day, what's happening is we're taking the absolute value of that thing. So now what we can do is we can cross off our k's, and all this has to be less than 1. So this becomes the limit as k approaches infinity, and you'll notice the k has disappeared once again. The negative symbol we'll deal with in a second. So we're left with negative absolute value of x minus 7 all over 3, and then that has to be less than 1. But the absolute value will take care of that negative symbol. And then all of a sudden, what are we left with? Well, we're just left with absolute value of x minus 7 over absolute value of 3. We can multiply both sides by 3, and you get the absolute value of x minus 7 is less than 3. So that tells us a radius of convergence. And usually we denote that by r, so radius of convergence is r equals 3. Okay? Yeah, so a great question. Is the point in putting that less than 1 to signify it isn't actually 1, therefore being inconclusive? Yeah, so we always do the less than 1 because that we know it will converge. This is a radius of convergence, so we know for certain that it'll converge there. And what the interval of convergence is doing is just checking those endpoints when it equals 1. So what we're getting with the radius of convergence is all the values where we're absolutely certain right away that it is going to converge. The interval of convergence, that's where we check those endpoints where it equals 1. That's essentially the one giving you more information is the interval of convergence. But sometimes we don't really care about the endpoints as much because we might be working with what we're going to do actually, by the way, is we're going to start writing functions in terms of these power series. and you'll see that actually later on here today, and I'll show you what we can do with that. And then if we have the radius of convergence, we can know, okay, this is about how far we can go. And so if we're looking for values within a certain range, we're going to be good to go. And sometimes we'll need to check those endpoints because maybe we want to extend, say we're trying to evaluate an integral or something, and it extends to the far endpoint of the interval of convergence. Those would be the cases where we're worried about it. But mainly the radius of convergence will give us enough. Especially we'll run into cases where the radius of convergence will be equal to infinity. And then we know it will match for all values of the function. So that's the beautiful thing. That's what we're searching for in an ideal scenario. So we'll see plenty of examples coming. We're going to define, I think today we're going to do like a natural log, one that involves a natural log, one that involves an arctangent. How do we define those functions in terms of these infinite sums? So that's our main goal for what we're looking for. So now in this, and great question on that. Yeah, so now we're checking equal 1. So for the interval of convergence, notice since r equals 3, we can use this to know that negative 3 is less than, possibly equal to, I'll put the question mark underneath there, x minus 7 now instead of just x. That's less than or possibly equal to 3. So what that means is we're going to check, when you add 7 to both sides, you get 4 is less than or possibly equal to x, and that's less than or possibly equal to, add 4 to this side, you'll get, or not 4, I'm sorry, add 7 to this side, you'll get 10. Okay, so we got to plug in 4 and 10 into our original and see if that works for the interval convergence. So when we have x equal to 4, what happens? Well, we get a summation k equals 0 to infinity of negative 1 to the k, and it goes 4 minus 7, oops, 4 minus 7, I was getting a little ahead of myself there, to the k over 3 to the k. So notice that becomes equal to the summation k equals 0 to infinity. I have negative 1 to the k, I have negative 3 to the k, and then we have 3 to the k. Well, the negative 3 over 3, and both of those are raised to the k, that's another negative 1 to the k. So this is summation k equals 0 to infinity of negative 1 to the k times negative 1 to the k, which is also, it can be written as negative 1 to, oops, I'm probably going outside my range there. That's also equal to the summation k equals 0 to infinity of negative 1 to the 2k. Well, when you think about that, that actually equals, and I'm showing a lot of work here, if you practice this enough, you get the hang of it and you can do it real quick, but this is a summation k equals 0 to infinity. When I take any negative 1 and I square it first, it doesn't matter what happens after that because I get 1, and so 1 to the k would be what happens there. Now, oh, my apologies, so some of that kind of didn't get written all the way through. So the piece that I wrote up there, let me write it off on the side here, my apologies. When k equals 4, and hopefully that makes it better in terms of what we're looking for. All the rest is just summation, so all I wrote is when k equals 4 up in that part. So that's all we're plugging in, or x, not k equals 4, my apologies, when x equals 4. Okay, so and can we see that now? My apologies about that, running out of the space. So now you have the summation k equals 0 to infinity of 1. This is divergent by the test for divergence. And you'll start to catch these trends. This one only has like numbers involved along with the x minus 7, so there's no k where we're doing stuff with that down in a base. So from there you can start to see real quick that these are going to diverge in these cases. So we're starting off with some easy ones, but I wanted to show you how we can shift and do things like that. The limits aren't real difficult just yet. They will get difficult though. So it can be a little bit more challenging in those cases. When x equals 10, you get summation k equals 0 to infinity. We get -1 to the k, and then we get 10 minus 7 raised to the k over 3 to the k. Well, notice that's just 3 to the k over 3 to the k, so that's a little bit simpler. We get summation k equals 0 to infinity of -1 to the k, and then that's just 1 over on the other side, so we'll just leave it as that. Well, this is divergent, so diverges by the test for divergence. And you're also done with that one. Okay? So now what that tells us is 4 didn't work and 10 didn't work for the equal to part. So our interval of convergence is just 4, 10, where they aren't included, so we put parentheses. So you might be thinking, oh, do we ever have equality? Well, yeah, we'll be getting to a few cases here real soon. So our next one, one that we'll look with, and so give us maybe a different radius of convergence and things like that. Let's take a look at this one. Now we have a factorial down below, so probably the root test isn't going to work as well. All of these, though, with the power series, you're starting with either a ratio test or a root test. So this case will be a ratio test. So how does that go? That goes limit as k goes to infinity, since we're using k, of a sub k plus 1 all over a sub k. And so that becomes, oops, sorry, once again got ahead of myself. We want this to be less than 1 at the end of the day. And so this is our test for the radius of convergence. So this becomes the limit as k approaches infinity of a sub k plus 1. Well, so notice we're going to take all the k values and put a k plus 1 in parentheses there. So we get k plus 1, the quantity squared, x to the 2, put it in parentheses, that's the big trick to this, 2k plus 1, all over k plus 1 factorial, and then all that goes over a sub k, so which should be the original term. So k squared, x to the 2k, all over k factorial. And all that should be less than 1. Yeah, factorial equals ratio. Yeah, majority of the time. There will be cases I can give you, say I raise the factorial to the kth power, then, well, maybe that needs a root test or something like that. But for the most part, yeah, just if you see factorial, the ones you'll see in this class at least, you're talking stuff that'll be ratio test if you see a factorial in there 9 times out of 10. So, yeah, keep that in mind when you're working a lot of these. So, working on this now, we can rewrite this as something a little bit nicer here. So let's do limit as k approaches infinity. When you divide by a fraction, you can multiply by its reciprocal, but not only will we do that, let's line up the terms that make it nice. So for example, we have a k plus 1 squared up top. Probably the nice thing to go with that would be a k. So we have k plus 1 squared, k squared. The other one, let's see, we have x to the 2k plus 1. I'll write it this way for now. And then we have an x to the 2k. And then the other one we'll have, it goes a k factorial will flip up to the numerator, but the k plus 1 factorial will stay down in the denominator. Okay. And this is all less than 1. Well, taking a look at this, you can rewrite this as a few different limits. Limit as k approaches infinity. And we'll have k plus 1 over k, the quantity squared. That'll be a little bit easier now. Notice x to the 2k plus 1, that's 2k plus 2. So that's times, when you take 2k plus 2 and then subtract off the 2k, because you can subtract those exponents, you're left with x squared. And then the last one, we'll write this as k factorial, and then the trick for the k factorial is k plus 1 is the first term. The next term, if you were to write k plus 1, it goes k, then k minus 1, so on and so forth. Well, k, k minus 1, and so on and so forth, that's just k factorial. So notice the k factorials will cancel. We want to see when this thing is less than 1. So what we have is we have the absolute value of x squared. We'll pull out in front. That's essentially the only part that doesn't have a k involved. And so we have the limit as k approaches infinity. Let me write it this way. The absolute value, since all this is multiplication, that's the reason I can pull that absolute value out as well as we just did. And we can bring the limit on inside. So limit as k approaches infinity of k plus 1 all over k. And I'm showing some extra steps right now. If you feel comfortable without it, that's awesome. And you can cut yourself some time-saving techniques there. And then you have 1 over k plus 1. And I forgot to write the limit once more. So times the absolute value of the limit as k approaches infinity of 1 over k plus 1. And then we want this to be less than 1. Well, when we take a look at this shindig right inside here is going to be 1. Right? But here's the big one. Our winner chicken dinner here. We get 0 right there. Limit as k approaches infinity of 1 over k plus 1. That will always equal 0. So with that in mind, if I take x squared times 0, it doesn't matter. That's still going to 0. I get 0 is less than 1. Well, that is always true. So what that tells us, that's a big piece of information. In terms of the radius of convergence, if you get the whole limit goes to 0, that tells you right away that r equals infinity. Okay? If r equals infinity, then what happens? Well, that means the interval, and actually I'll write interval of convergence. Goes from negative infinity to positive infinity, and you're done. Anytime you have a radius of convergence equal infinity, that means the interval of convergence is all real numbers. So that means this series will always converge for every single real number. There's going to be a few of these that pop up over and over again, so we're going to see stuff like this happen quite a bit. Okay, questions on that one? So now, actually, I might avoid writing that less than 1 on the first few steps, and so we can just kind of try and evaluate a limit and see where we can go from here. So, you tell me, what would you prefer, ratio or root test on this one? Let you kind of decide what you want to see, ratio or root test. Either way, we're going to have a limit as n goes to infinity, so. Root test. Okay, sounds good. And that's actually going to be your most efficient method, and that was perfect. Since you have an nth power here and an nth power there, and there's no n's down below, even if there were, it's a lot easier to work with this. So that was a great choice. Get x plus 2 to the 2n over 10 to the n. And so an easier way for us to write that, and as I said, I'll just drop the less than 1 on every step. Hopefully that makes sense. If it does bother you a little bit, let me know. Just remember, less than 1 is something that we're going to do. So yeah, that's exactly the right choice in terms of nth root. And so now we can write this as x plus 2 squared all over 10, and then this whole thing is raised to the nth power. So now we have something canceling, and we have the limit as n goes to infinity of, notice this is just the absolute value of x plus 2, the quantity squared, all over 10. Right, because absolute value of 10 is just 10. So notice though, there's no n involved. So what this becomes is the absolute value of x plus 2, the quantity squared, over 10 is less than 1. Which does imply that we have x plus 2, the quantity squared, is less than Okay, now what do we do? Well, if we want that to be less than 10, let's see how we can rewrite this. Well, first off, in order for this to be less than 10, you could do it one of two ways. You could do this whole -10 less than x plus 2 less than 10, or x plus 2 the quantity squared. And you can remember that this is always going to be positive since we're squaring it. Well, at the end of the day, is -10 going to be in play at all? Well, not really. I mean, it's not going to play an impact factor here. So what we're actually looking at is, yeah, we can say this goes all the way to -10, but at the end of the day, this bound down below, oh, by the way, if you are to work with this now, if you want to find the radius convergence, I was hopping to the interval of convergence. Let me scoot back here real quick. Okay, so how do we solve for this? Well, you have x plus 2 is less than 10, or an easy way is to take the square root, so you get absolute value of x plus 2 is less than the square root of 10. Okay? And at the end of the day, what happens there? Well, this means you have a radius of convergence. Is r equals the square root of 10. Now you might be concerned because usually when we take a square root, there should be a plus or minus involved, right? But once you think about this, if I go to minus square root, the absolute value being less than minus square root of 10, notice that doesn't even make sense in terms of we have a positive number, we can't have that be less than the negative. But we would kind of switch the sign and we'd get absolute value of x plus 2 is greater than negative square root of 10, which is what we're going to get for free anyways, right? We're going to get that with this bound, so that's good. We're in good shape. There's no problem points there. But what does happen is now for the next part we get negative square root of 10 plus, or is less than absolute value of x plus 2, or not absolute value anymore. And that's less than the square root of 10. So notice that gives us a range of -2 minus square root of 10 is less than x, and then it goes less than -2 plus square root of 10. There's a possibility for equal in either case. But hopefully we can start to see what's happening now. So when x equals -2 minus square root of 10, hopefully we'll see real quick what happens. Notice we get a summation n equals 0 to infinity of, this would become -2 minus square root of 10 plus 2 raised to the 2n all over 10n. Well, notice that becomes, you'll have the -2 and +2 cancel. You'll have a negative square root of 10 raised to the second power, so this just becomes 10 raised to the n. So this is summation n equals 0 to infinity of just 1. Once again, we know this diverges by a test for divergence. Okay, so in that other case, when x equals -2 plus square root of 10, it isn't going to make much of a difference. You get the summation n equals 0, and then you'll have -2 plus the square root of 10. But remember, we're going to square it, so we're going to have the same exact thing happening. Plus 2 raised to the 2n all over 10 to the n. That also equals the summation n equals 0 to infinity of 1, which diverges by the test for divergence. And why does it, I should clarify too, I'm saying diverges by test for divergence. When you're doing that, you're just taking the limit as n goes to infinity of whatever's inside the summation. So the values that you're looking at, a sub n's, in this case it's 1, so it diverges because of that value there. Okay, so we've done some interesting ones. Now it's going to get a little bit heavier here. When we look at this summation, n equals 1 to infinity of n to the nth power, x to the n power, and then n plus 1 factorial. When you take a look at this, what do you think we should use in order to solve this one? What's our approach? And once again, it's going to be a limit as n goes to infinity. And this is the hardest part. I mean, once you kind of get that and get rock and rolling, maybe some limits every now and then, but we can still solve it either way. So what do you think? Is this going to be a ratio test or a root test? Ratio is right. That's right on the money. So this one, you have a sub n plus 1 over a sub n, and the dead giveaway was that factorial down below. So this one once again becomes limit as n goes to infinity, and there's some shortcuts you can take on this as well, but notice we have n plus 1, and then you're also going to have an n plus 1 up there. You have x to the n plus 1 all over goes n plus 1 plus 1 factorial. So a lot of stuff going on right there. And then we have n to the n. We have an x to the n. And we have an n plus 1 factorial. Okay. So this thing, once again, we're going to go back and say, hey, this has to be less than 1. We get the limit as n goes to infinity. Okay, now here's where things get fun. Let's rewrite this a few different ways. So we'll have n plus 1 to the n plus 1 power all over n to the nth, because those kind of match up, right? We'll have an x to the n plus 1 over x to the n, and we'll have what's the other one, m plus 1 factorial, and then the m plus 1 would be m plus 2 factorial. Yeah. So, and you keep on looking at this. Now, what do we have here? The limit as n goes to infinity. This one's kind of crazy, right? Right there. Let's rewrite it so we can handle it. The way we can rewrite this is n plus 1 to the nth power times n plus 1. Okay, what does that do for us? Well, that allows us to rewrite this as n plus 1 over n, because both of those are raised to the nth power, and then times n plus 1. Okay. The next one, the x to the n plus 1 and x to the n, you can subtract the exponents, you're left with just x to the first power. And then the last piece, we'll write n plus 1 factorial. And n plus 2 factorial is just n plus 2 factorial, or n plus 2 factorial can be rewritten as n plus 2. The term before that's n plus 1, and we can count it out down to get n plus 1 factorials. Okay, so this looks all sorts of crazy right now. And let's try and see what happens here. So we get limit as n goes to infinity. Now what do we do? Well, we can rewrite that first one as 1 plus 1 over n raised to the nth power. I'm going to do some regrouping here. So this is times n plus 1 over n plus 2. All I did is I moved this piece and this piece together in one fraction. And then times some x. Okay. Moving forward from here, what do we get? Well, notice when you do this, you get 1 to the infinity is what it looks like, but that's actually going to be a little bit trickier for this limit. And to be honest, I might only be able to fit the radius of convergence on here, so kind of keep that in mind. I might have to stop. I'll try and fit everything I can, but just from a room standpoint, just do the radius. That's the main thing in this case. So we have the absolute value of x. We can pull that out and just check out these limits. So we have the limit as n approaches infinity of one part that's going to be easy is this n plus 1 over n plus 2. Okay. The other part, though, we are going to need to use some tricks. Since you have an n on the inside and an n on the outside, you have to use this e trick. And so it goes e to the natural log of 1 plus 1 over n raised to the nth power. Right? So that's one of the old tricks that we used with L'Hopital's and things like that. And so moving forward from there, we'll get the absolute value of x and that first limit. So this whole shindig, n plus 1 over n plus 2 as n goes to infinity, that thing just goes to 1. So times 1. Next one, though, that's not going to be as nice. So in fact, we have e to the natural log of, this is positive always, so we can actually even drop the absolute value if we want at this point. So we can write e raised to the limit as n goes to infinity. We can bring it up in the exponent now, and we can bring down the n in front, but that doesn't do much for us either. We have infinity now times 0. So the way to write that so we can actually work with it is natural log of 1 plus 1 over n all over 1 over n. And what that allows us to do is use L'Hopital's rule. And so we have absolute value of x times e, and L'Hopital's rule says, okay, this thing looks all sorts of crazy, but we can write this as 1 over 1 plus 1 over n times the negative 1 over n squared, okay, from the derivative of the top, and then the derivative of the bottom is just negative 1 over n squared. So notice that cancels off, right? And we're left with this limit as n goes to infinity of 1 over 1 plus 1 over n. So we get the absolute value of x times the, what do we have there? That's going to be the limit as n goes to infinity of 1 over 1 plus 1 over n. And so this whole thing equals, notice this goes to 0. So we get absolute value of x times exactly what we think about beforehand, I'm sure, e. So remember, though, that we have absolute value of x times e is less than 1, right? In order for this to satisfy the ratio test. So absolute value of x is less than 1 over e, which I think is kind of crazy when you start to look at this stuff. I mean, maybe that's just me, but it's really kind of nuts where an e can get involved in your radius of convergence. So what we have is our final answer. I'm sorry for running out of room here, but the radius of convergence will be equal to one over e. And so from a room standpoint, I'm not going to fit interval of convergence on here too nicely. I'll have you try the interval of convergence on this one, see if you can figure out what that is. But the nice part is you can combine that. You'll have now n over e raised to the nth power, and then n plus 1 factorial. You'll have to do some sort of checking on how you can solve that, but hopefully figure out a nice result from there. Yeah. Okay, so I see a question here. I guess what I am confused about is what is actually new that I am applying. It seems the exact same as we have been doing. Yeah, and that's exactly the only thing that's new in terms of, I'd say, what you have here is the fact that e can pop out of one of these limits. So it's just an old limit. It's the same old song and dance in terms of that stuff. The only thing that's really new is the fact that we're starting to define functions in terms of these x variables. All right. You might not have done so much on the power series representing functions in terms of power series, but that's actually coming up, and that's what we're building to. I want to make sure that we understand this first, and then we can define when this function that we're going to talk about is going to match up to these. And so that's the whole trick with the power series idea is you're going to use the ratio test, you're going to use the root test. That's the same song and dance that we did before. Well, yeah, we have an x involved, but we want to try and define functions and determine where are these things going to be working in terms of matching up. What is the function going to equal this power series? And that's what the radius of convergence and interval of convergence will tell you. So does that make sense, or did I lose you kind of along the way, or just, yeah, please let me know. Yeah, there's really no new tricks other than we're just using the ratio test and root test. We're just defining x as some variable now is the main point. So that's all there is to it. But this tends to be one of the toughest parts of Calc 2 for most students. I'll be honest. Historically, from when I've taught it and talking to other professors, this is really the part that trips up people, is this power series business. So if you're grasping this, you're going to be in good shape in terms of what's coming on down the road. So yeah, moving forward from here, we have more of kind of the same song and dance. So I want to see that. Let's give this a shot, and then we'll kind of start. I think we have one more that we're going to work out, and then we'll start to move on to actually finding the functions in terms of power series, how we can work those things. So this thing, same old song and dance. We have the limit as n approaches infinity. Ratio test or root test, what do you think on this one? Yeah, we can work with a ratio. So if I do the a sub n plus 1 over a sub n, we can work with that. I will give you a little hint though. Notice you have an n, an n, and an n there. That might have given you a clue as to what we're going to come down and see in time. But we can work with the ratio. I'll show you how that goes. We get an x minus 1, and I'm actually going to start to write this slightly differently. If this gets a little bit confusing, let me know. I'll be happy to slow it down. What happens is with the ratio, if you're taking a sub n plus 1 over a sub n, anything of the numerator over the denominator, so if I have x minus 1, it'll be n plus 1 up top, and then down below I'll have an x minus 1 raised to the nth power. So just to show you a different way of kind of, yeah, so the nth power does mean, since they're all the same, that probably would work with the root. And I'll try and fit that on here. As I said, I might leave the interval of convergence to you to work out and whatnot. Yeah, so the n in the denominator, right, that's a great question. So the question was, I was thinking of the n in the denominator, it would be ratio instead of root. And that's usually the case if we had a factorial. Since it's not a factorial and everything is an nth power, and it's just a straight up nth power, that would work to take care of all these nth powers real quick. And so if you have everything raised to nth power, we could have rewritten this whole summation as a summation n equals 1 to infinity. And that's a real trick to a lot of these. We could write this as x minus 1 times 3n all over n plus 1 raised to the nth power. That's the same thing, right? And so that's why we want to try and kind of look at, hey, is there another way we can rewrite these summations? So, and I want you to see the ratio. It's good to see that. Yeah, you can do the root and kind of work it that way. We'll see both just to kind of set it up and show you what's the difference in terms of these two. So the next one, we'll have 3 to the m plus 1 raised to the n plus 1 power, and then that's all over 3n raised to the nth power. And then we have an n plus n plus 1 raised to the nth power. Notice that denominator will come on top now, because the one where we actually add an extra one, the n plus 1 raised to the nth plus 1, that should appear right there. Okay? So this thing equals the limit as n goes to infinity of, we'll have an absolute value of x minus 1, and I'll start breaking up the absolute values as well because that'll be a little bit easier. So we'll have, this can be rewritten as, I'll leave the 3 to the n plus 1, but we'll go to the n and then times another 3 and then an n plus 1 there. Okay? So that makes, this is 3 to the n plus 1 raised to the n times 3 to the n plus 1, and I don't even need that extra parentheses around that second one, but you can put it if need be. And then we have a 3n raised to the nth power, and so that'll allow us to group those two things, times another, same thing here, we're going to have an m plus 1 raised to the nth power, and we can rewrite this thing as m plus 2 to the nth power times m plus 2. Okay, so now we'll see why this is going to be a little bit harder. So, and I can pull the x minus 1, that absolute value, out in front. Times the limit as n goes to infinity of, so this is 3n plus 3 over 3n raised to the n. When looking at that, you can take that limit. You're going to need to use an e to the natural log power, right, of that quantity, and that'll kind of explain why this is going to be a little bit harder. And you'll have a 3n plus 3 over n plus 2, and then you'll have an n plus 1 over n plus 2 raised to the nth power. So both of these, you're going to need to do that e to the natural log thing. Now if you practice that enough, you'll be able to see it very quickly, right? And I'm going to leave that part to you, and I'm going to show you how the root test kind of works from here to kind of give you an idea as, okay, what happens. So, but what I mean by the e to the natural log, you'll take an e to the limit as n goes to infinity of the natural log of 3n plus 3 all over 3n raised to the n, right? That allows you to bring this n on down, and then you'll have, okay, so what does this become? This becomes natural log of 1, which is 0, and then over, you'll have to rewrite this as 1 over n. So e to the limit as n goes to infinity of the natural log of 3n plus 3 over 3n, and then over 1 over n. And then you'll have to work that and keep on going. Yeah, and so that's the whole idea with this, is you're going to have to use that e. You're going to have to work with that, just like we did on the previous one. The e came into play. If you're using the ratio test, that's going to be necessary, and that's actually going to happen anytime you have an n in a base and an n in the exponent. So meaning the base and the exponent are the same as your index. That will always happen if you're using the ratio test. You're going to involve the e in the natural log, just like that last one. So now, but this one we were kind of fortunate in terms of having the root test, and I'm going to actually erase this part, and hopefully you can kind of take it from there to finish that off. But I'll show you how the root test works, just to kind of give you an idea in terms of what happens. So I'll work with that second notation where we have everything raised to the nth power already, and we'll pull that out there. So this is the limit as n goes to infinity. Once again, the nth root of the absolute value of a sub n. So this is the limit as n goes to infinity of the nth root of x minus 1 times 3n all over n plus 1, and it's raised to the nth power. Notice now, and let me put an absolute value there, the nth power here, or nth root of the nth power, those will cancel, and so what we're left with is just the limit as n goes to infinity of the absolute value of x minus 1 times 3n all over n plus 1. Okay, so now we can pull that absolute value of x minus 1 out in front, and then we'll have the limit as n goes to infinity of 3n over n plus 1, which just equals 3 for that limit. So this is the absolute value of x minus 1 times 3. So that becomes, remember, this has to be less than 1, so I'll write it this way. 3 times the absolute value of x minus 1 is less than 1. So that means the absolute value of x minus 1 is less than 1/3. Okay, so whoop-de-doo, right? But we have the radius of convergence is given by r equals, let me put a colon there, r equals 1/3. So now, if we're looking for the interval of convergence, that means negative 1/3. I'm not sure if I'll probably be able to fit this in here, is less than x minus, whoops, I can drop the x minus 1's absolute value symbol, so this is x minus 1, and that's less than 1/3, with the possibility of being equal. And so I'll put the question marks down below, and we'll see what happens. So now, where do we go from here? Well, add the 1 to both sides, and you'll get 2/3 is less than or possibly equal to x, and that's less than or possibly equal to 4/3. So let me write up here, when x equals 2/3, what happens? We get this summation. Plug in 2/3 for the x. I'm going to make that a little bit more simplified. We get negative 1/3 let me write it 1/3 times 3n all over n plus 1, and that's all raised to the nth power. Okay, the negative 1/3 and the 3 will cancel, and you're left with just the negative n over n plus 1 raised to the nth power, right? And so this thing, summation n equals 1 to infinity, we can pull the negative 1 to the n out. So negative 1 to the n, and then we're left with an n over n plus 1 raised to the nth power. Now, you can check, you might not recognize that limit, but limit as n goes to infinity. I'm just going to look at the positive terms, because remember, alternating series test says we have to look at something like this. Well, the way we do that, once again, is we do e to the natural log. So you bring that out in front. So we get e to the natural log. Or actually, let me put the limit out front there. So you have limit as n goes to infinity of natural log of n over n plus 1 all over 1 over n. And so we'll have to go through this rigmarole in terms of what is this going to become. Well, this is e to the limit as n goes to infinity. We get a negative 1 over n squared down below. And up top, though, you're going to basically natural log will be 1 over n plus 1. But we can just flip-flop that, make it n plus 1 over n, and then times the derivative of that. Well, that's not always the nicest thing to deal with, but we can still deal with it. n plus 1 squared. You bring the n plus 1 up top, and that becomes n plus 1, and then minus, and then it goes basically n in that second position. And so the n's will cancel, and you're left with 1 over n plus 1, the quantity squared. Okay, so if you take a look at that, there's going to be a whole bunch of canceling going on here. So the n plus 1 squared will cross off with the n plus 1. You'll have a negative n squared kind of flip-flopping up top. So this thing becomes the e, limit as n goes to infinity, of negative. We'll have one of the squares will cross off with the n. So this becomes n over n plus 1. Notice that equals e to the negative 1, which means at the end of the day this is just divergent. By the test for divergence. So at the end of the day we have 2/3 won't work. And you can see, actually, there's a similar result that you can have. And the fact is that that's not 0. It has to be 0 for even to have a chance at it converging. So the other scenario, though, when x equals 4/3, just an FYI, you'll get the summation n equals 1 to infinity of 1/3 times 3n all over n plus 1 raised to the nth power. And notice that just becomes summation n equals 1 to infinity of n over n plus 1 raised to the nth power. So now we have just the positive version of that versus the negative, but same difference. This is also diverging by the test for divergence. So that means this won't work, and that means our interval of convergence is given by 2/3 to 4/3. Okay, so that kind of shows you how we can get some things that look pretty crazy at times and how that works out. This one, and I think this is our last one before we move into the power series representing functions in terms of them. In the case of this, what happens? Well, you get summation n equals 0 to infinity of this n to the 20th. Well, we can use, since we have a factorial and it seems like we're catching on here, we can use the ratio test. So you get a sub n plus 1 all over a sub n, and so this would be the limit as n goes to infinity of, it goes n plus 1 to the 20th. And what we'll do is we'll actually write them separately. If you don't like this format, please let me know and I'll be happy to write it the other way, but just kind of trying to break it on down piece by piece. If you struggle with this, though, if you aren't sure on what goes on top, what goes on bottom right away, I'd strongly suggest taking that extra time and writing it out the first way, then multiplying by the reciprocal. So now this part gets a little bit tricky. You have a 2n plus 1 factorial down below, because that's where, when we add the a sub n plus 1, it should stay down below. And then up top would just be the original term, the 2n plus 1 factorial. Okay, so a whole bunch cancels and we can move some things around. So this, first off, you'll have the ends will cancel for that, and so you'll just be left with x to the first power along with the absolute value. Notice that doesn't involve an end, so we can just pull that out in front. The next part isn't so bad. We have the limit as n goes to infinity, and then the absolute value on this, it's not going to make a difference since we're talking positive values. So we have m plus 1 over n raised to the 20th power. Luckily that's a finite number, so that's going to be easier. We can pull this limit on the inside. And the other one, notice this is 2m plus 3 down below. So we get the limit as n goes to infinity of 2m plus 1 factorial. But 2m plus 3 factorial, let's write as 2m plus 3. The term before that is 2m plus 2. And the term before 2m plus 2 is 2m plus 1. But we can count on down from there, so we can write factorials. And we can cross off those factorials. And the beauty on that is we know that we'll have the absolute value of x in right there, times the second limit will just be 1. And the third limit, we have 1 over just some stuff going to infinity. Well, that's 0. So this whole limit, regardless of what x is 0, and that is always less than 1. So that means our radius of convergence is r equal to infinity. So that means the interval of convergence is negative infinity to positive infinity. So keep that in mind. One of these things, I should go back before I actually move forward. One little comment. I didn't go through any where the radius of convergence doesn't work, so where it always has a greater than 1 as a number. There can be cases of that, and what actually happens is we say the radius of convergence in those cases is equal to 0, and the interval of convergence is just the point where whatever's x, if you have x minus, say, some c, it'd be where x equals c. There's just one point, and that's the only interval of convergence, is a closed point. So that can happen as well. Just kind of keep that in mind. That's the tricky case that you run into from time to time. If you want to see one like that, I can do that too. That isn't too hard. In terms of what we really want to start doing, though, is finding power series representations for functions. And the real trick to that stems from where we have 1 over 1 minus x. That equals the summation n equals 0 to infinity of x to the n. Right? If you recall that. So if we have that fact that this 1 over 1 minus x equals that summation, we're going to be in good shape. Okay, so how does that work here? Oh, and I should say where the absolute value of x is less than 1. Right? That's what we had for, this was just the geometric series. And that's all we're going to be using here, is the geometric series. And so we can cut down actually on our time too in terms of ratio test if we have just an x involved or some multiple times x. It does get a little bit trickier when we start to have ends and things like that involved. So like in our formula, you'll see some scenarios of that soon enough. So in this first case, if we want to represent f of x as a power series, notice instead of x we have 5x. So whenever we have an x in our formula, we're going to plug in a 5x. So this becomes a summation n equals 0 to infinity, and then it says 5x raised to the nth power. Right? So another way to write this, though, just so you might see how this has some connections to what we did before, this is 5 to the n, x to the n. Now, I can use that first idea, though. Using this term, I can say where absolute value of 5x is less than 1, or where the absolute value of x is less than 1/5. So that actually tells me, without doing all the extra work in this case, what the radius of convergence is. The radius of convergence must be r equals 1/5. We can go through that, and we can do this with the ratio test. We could do it with the root test. you're going to get the same results. Okay, either way. The beautiful thing is, though, just the fact that it's a geometric series, we have no n's down below. The n is just in the exponent. We can cut to the chase and get done with this really quick. Okay. Questions on that? That's our first kind of go-to. And that's the main goal of this. We want to start representing functions in terms of power series. And by the way, so what does that mean? For everything, now I didn't check the endpoints, but you can check the endpoints and see that the interval is actually going to be from -1/5 to +1/5. When you actually do that, if you pick a number that x is between -1/5 and +1/5, this function right here and this power series right here will give you the same exact value. Okay. So say I wanted to do something like 1/1 minus 5 times, well, something less than 1/5, so say 1/7, 5 times 1/7. I can calculate that, but I can also calculate in terms of the sum. If I'm trying to do an approximation, I could do a decimal approximation of some sort, right? So you can really get some pretty neat answers without using a calculator using these series. So next one, g of x, we can use a similar idea. So we still want to use that geometric series, but what we'll have to do right now as written, we can't use it. So we'll rewrite this as 4x cubed times 1/1 minus x. Well, that thing is the same as 4x cubed times the summation n equals 0 to infinity of x to the n. Okay, the beautiful thing is 4 is times every single thing in here. So in x cubed is times every single thing in here. So you can rewrite this series. You can bring those things inside the summation. And so you get 4x cubed times x to the n. And now you have the summation n equals 0 to infinity of 4x to the 3 plus n. Or n plus 3. Right, either way. At the end of the day, though, notice the 4x cubed, yes, we did bring those in. But at the end of the day, we had, here is the point where we have to be concerned for a convergence. So this is where, well, when does this occur? Where absolute value of x, this is a geometric series, so that's where the absolute value of x is less than 1. And we're done. If you use the ratio test on this, you'll actually get the same exact thing. You'll get where the absolute value of x is less than 1. Only thing to be careful on if you use the ratio test is the fact that the 4 does not have a power on it. So you're going to have 4 in the a sub n plus 1 and the a sub n. It's just going to be 4, not 4 raised to some power. So what we have in this case, radius of convergence, is r equals 1. Right, so the geometric series is doing some heavy lifting for us now. It will get harder, though. I will say that. Okay, so 1 plus 4x. What does that thing look like? Well, another way for us to write that is h of x equals 1 over 1 minus negative 4x. So notice that means when we write this as a power series, that's the summation n equals 0 to infinity, and we put the negative 4x raised to the nth power. Okay, well, if we try looking at that, where do we go from here? Well, we have where absolute value of negative 4x is less than 1. Notice when I take the absolute value of negative 4, I get the absolute value of x is less than 1/4. Right? So that's one way to write it. Another way, what you might see quite often, is summation n equals 0 to infinity of, this would be negative 1 to the n, because of the negative symbol there. You can have a 4 to the n and an x to the n. Personally, I think the negative 4x raised to the n looks great, but this might be another format. And then where you have absolute value of x is less than 1/4, or what we can say at the bottom is radius of convergence is r equals 1/4. Now all these cases, interval of convergence, you're not going to have anything special happening there. It's just going to be from the negative r value to the positive r value if we're talking x in each of these, and we have no endpoints included in those cases. So the real interesting stuff is coming up when we start defining other functions. Okay, so what's the big deal here? Well, with the 1 minus x, finding a nice sort of power series representation of this thing as is might be kind of hard. But there's one extra caveat that we can kind of work with. This cube prime of x, what does that equal? Well, that equals 1 over 1 minus x times -1, right? So that equals, I'll move the -1 here, -1 times 1 over 1 minus x. So the beautiful thing here is, though, we know that this is the negative and then the summation n equals 0 to infinity of just x to the n. So far so good on that part? Because here's where things get kind of crazy. So I can pull the negative symbol in, but notice it's not a -1 to the n. It's just a negative symbol out in front of that. But if we want q of x, notice that would equal something similar. We'll be careful here. I'm going to write q prime of x dx, but that's not completely true. So that means that we can take the integral of this negative summation n equals 0 to infinity of x to the n dx, right? And so the beautiful thing here is that when we have an integral, and remember, summation, that means plus, plus, plus. We can move the integral to each part of the pluses, right? So you can rewrite this as the negative summation n equals 0 to infinity of this x to the n dx. Right? So that means at the end of the day we get negative, and we'll have a summation n equals 0 to infinity of, well, what's the antiderivative of x to the n? Well, it's 1 over n plus 1 x to the n plus 1. Right? But now I have to toss in one extra caveat. So all this junk, and then I have plus some constant c, right? Because I took an integral now, I have to account for the constant c. So that sounds tricky, right? Well, not so much. So I have natural log of 1 minus x equals something like this. So it's negative summation n equals 0 to infinity of 1 over n plus 1 x to the n plus 1, and then we got plus some constant c. How in the heck are we going to figure this out? Well, the easy way for us to figure this out is let x equal 0. Okay. So if we let x equal 0, what actually happens? Oh, and I should be careful here. Notice what happened as well. When I took the derivative, it's actually going to be a little bit trickier later on down the road when we do take derivatives. The index, I left it as n equals 0 because think of our first term. Our first term is just 1, essentially, and -1, I should be more specific. And then so our first term here, when you take the antiderivative of -1, you should get negative x. Well, that's okay. We get negative, and then we get plug in 0, so you get 1 over 1, which is 1, and then x to the first, so negative x. That's exactly right. And so we're matching up in terms of our index and what happened. When you take the derivative, though, if we take the derivative of power series, which we'll do later on, we'll run into problems with that. We'll have to start changing indexes, like if we have the power series and we take the derivative of that first. So keep that in mind coming down the road. So when we do this x equals 0, though, we get negative summation n equals 0 to infinity. I don't know much, but x raised to the n plus 1. If x is 0, that's a 0. So this is 0 plus c. And so that means natural log of 1 equals c. But luckily, natural log of 1 is a 0. So 0 equals c. And so we have a beautiful power series in terms of this. It is just the summation, or negative summation. And then we have n equals 0 to infinity of, and I'll write it this way, x to the n plus 1 over n plus 1. Little FY, you might see this rewritten depending upon what you do. You can reindex this thing. You can go n equals 1 to infinity, negative, and then you can write this as x to the n over n. Notice our first term in either case, you get x to the first over 1, right? And then you get our negative x to the first over 1. In the second case, negative x to the first over 1. So either way, you can come up with the same result. Okay. So there's a couple ways to represent these power series, depending upon if you want to reindex. So now you saw how we found the plus c and all that stuff. So let's move forward a little bit more. Okay. So now, where do we go from here? Let's see. If we want to find the radius of convergence, we do have to work on this one a little bit. And so in this case, we will use the ratio test. Limit as n goes to infinity of a sub n plus 1 all over a sub n. So this equals limit as n goes to infinity. We have negative, well, the negative, by the way, we pull that out in front, so that's not even going to make a difference. We'll rewrite this as x to the n plus 1 plus 1 over the x to the n plus 1 times, and then we have m plus 1 going up top here, and then m plus 1 plus 1. And so that equals the limit as n goes to infinity. We'll just have an absolute value of x, and then we'll have m plus 1 over m plus 2, which luckily that whole thing right there just equals 1. So that means this is the absolute value of x, and we need that to be less than 1. So the radius of convergence in this case is r equals 1. Now, just a little FYI, in this case though, things get a lot more interesting on the interval of convergence. I wasn't asking for this, but I want to share it. If you plug in -1 in for x, notice you get an alternating series, and it's the alternating, essentially the harmonic series. If you look at that next term where you have x to the n over n, you can see that right away. So you have an alternating series where it's the harmonic, kind of like the harmonic series. So that's conditionally convergent. So in that case, what we get is, this thing's a lot more interesting. The -1 would actually be included, and the 1 would not. Try that out. Make sure you can do that. That's kind of a golden key. This is a big one that works over and over again. But yeah, give that a shot and see what happens too. So, alright, so we have the natural log of 1 minus x. That thing has a nice summation. I'll write it down again here. So this is negative summation. If we use n equals 0 to infinity, you can write that as, when we just did x to the n plus 1 over n plus 1. Okay. So now we want to find r of x. Well, notice that r of x equals x cubed times the negative summation of n equals 0 to infinity of x to the n plus 1 over n plus 1. Right? Now this is just multiplication, so we can bring that x cubed on in. And so we'll have, this is the summation n equals 0 to infinity. Oh, negative symbol there. So we have x cubed times x to the n plus 1 all over n plus 1. And that thing should equal the summation n equals 0 to infinity of x to the n plus 4 now, because you add the extra 3 in there, all over n plus 1. Yeah, so that formula of natural log of 1 minus x, yeah, you can definitely put that on the note sheet. That's one that pops up quite a bit. Along with the big ones that you're going to see coming up are e to the x, sine of x, cosine of x, arctangent of x. Those are going to be ones that are very useful in terms of what you'll see. So we're going into that when we get into Taylor series and Maclaurin series. You'll see the rest of them. So, but this is kind of the focus on a few of them for right now. You can use the ratio test once again. It's going to be the same song and dance. So ratio test, notice if I add 1 in there, so I get x to the n plus 1 plus 4 all over x to the n plus 4. So basically the n plus 4 and that would cancel, and you're left with just x to the first. The other case, you'll have an n plus 1 there and an n plus 2 there. So notice, well, let me be careful. Just so we can see it, we have an n plus 1 there, so it's the same song and dance. The only thing that you had is the x values changed. And so this thing equals limit as n goes to infinity of the absolute value of x times n plus 1 over n plus 2, which equals 1. So you get this whole thing equals absolute value of x, which is less than 1. The radius of convergence and the interval of convergence are identical. So radius of convergence is r equals 1. So once you have one of them, it's pretty straightforward. So now the arctangent of x is going to be something very similar. So notice everything we did today, we kind of worked with what are the original, like we got to take a derivative and then we work with an antiderivative. And so that's what we'll do here. We can notice that m prime of x equals 1 over 1 plus x squared, which might be a little bit trickier for us to work with. This is 1 over 1 minus negative x squared, which makes this one a lot more fun. So in this case, what happens? Well, that is the same thing as the summation n equals 0 to infinity of negative x squared raised to the n. And so what does that do? Well, we can rewrite this as a summation n equals 0 to infinity, and we have a negative 1 to the n and an x to the 2n sitting right there. But that's the derivative. So remember, if we want m of x equal to arctangent of x, we need to take the antiderivative of the derivative. So the antiderivative of the derivative, but we're going to get this extra constant c that we have to worry about. Luckily, this one will be nice. So now, what does this become? Well, this is the integral of the summation n equals 0 to infinity of negative 1 to the n x to the 2n. And so from here, oh, and I need a dx there. Remember, this summation and the negative 1 to the n, those are all constants in addition between constants. So the x is the only part that really we have to integrate. So you can pull out the summation n equals 0 to infinity of, and you can pull out the negative 1 to the n because that's just a constant. So we're left with this integral of x to the 2n dx. And so this is a lot more interesting because it gives us something that you might not see initially in terms of what's this going to work out to be. This is n equals 0 to infinity. You have a negative 1 to the n, and the antiderivative of x to the 2n is x to the 2n plus 1 all over that same power, so 2n plus 1. And then we need to add in that plus c, right? So now, when x equals 0, what do we have? We have the arctangent of 0. And why are we using 0? Well, it's because we have x raised to some power. We don't want to have a number in there that's non-zero. That's just going to be where you have to do a little bit extra work. Let's make our lives simple and figure out what this equals. So n equals 0 to infinity of, I'll write out the extra steps, but negative 1 to the n, this is 0 to the 2n plus 1, all over 2n plus 1, and then plus some constant c, right? So that means that arctangent of 0 equals c, or arctangent of 0 is 0, so 0 equals c. So the one you really want to write down in terms of formulas, you have this as a summation n equals 0 to infinity of negative 1 to the n, and then it's x to the 2n plus 1 over 2n plus 1. Now we got to figure out that radius of convergence. What the heck's going on with that one? So I'll erase the c part where we can kind of figure that out at least. And I'll just write on this line up above what we had. So this equals a summation n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 all over 2n plus 1. Okay, so now where do we go from here? Well, we can use the ratio test once again. No, not ration test, ratio test, and we'll get limit as n goes to infinity, and we'll have x to the 2, and then we'll have m plus 1 over 2, and, well, let me do this, over x to the 2m plus 1 times, we'll have 2n plus 1 over 2m plus 1 plus 1. Now you might say, well Josh, wait a second, where'd the negative 1 to the n go? Well, if I divide negative 1 to the n plus 1 divided by negative 1, it's gonna, to the n, it's going to be negative 1, right? But as soon as we take an absolute value of that, it just goes away. So you don't even need, if you have a negative something or other, you can just ignore that when you're doing the ratio test. That's why the absolute value is there in the first place. So in terms of what happens here, the numerator is 2n plus 3. So 2n plus 3 and then x to the 2n plus 1, that makes this thing will become x squared. So you got the absolute value of x squared times the limit as n goes to infinity of 2n plus 1 over 2n plus 3. Luckily, that whole shindig goes to 1, so what we're left with is this equals the absolute value of x squared, which is less than 1. That means the absolute value of x is less than 1 as well. So we have our radius of convergence, and it is r equals 1. Now if you want to plug that in, you can start working with, okay, what's negative 1? When we plug that in, what happens? When we plug in a positive 1, what happens? In either case, notice you have that you'll still have the negative 1 to the n. Negative 1 to the 2n plus 1, by the way, that's just negative 1 to an odd power, so it's always going to be a negative 1. So that basically you still have an alternating series in either case. And an alternating series, that means convergent in both of those cases, because you do have decreasing on the 1 over 2n plus 1. So you can check that out too and make sure that works on those. So now let's kind of work with this and see what happens. What can we do? So in terms of what we just had, you see the summation n equals 0 to infinity and negative 1 to the n x to 2n plus 1. So that's arctangent, right? Summation n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1, right? So you might be saying, whoa, wait, what are we doing here with this integral? Well, the beauty and the reason why we really enjoy this type of stuff is because when we have a nice hard integral, whereas we'd have to use integration by parts on this, and then we'd have to probably use, in the case of this one, we'd have to probably use partial fractions and all that. Watch how quickly this can go in terms of our integral. As long as I know what arctangent of x is, we get something like this, right? Okay, and then we have our dx. X to the ninth can go on inside. So this thing equals the integral, the summation, n equals 0 to infinity, negative 1 to the n. I'm going to pull out the 1 over 2n plus 1. And then we'll write this as x to the ninth times x to the 2n plus 1. And then a dx, right? So the only pieces here, or the x's, are right there. So the rest are just constants. So this thing equals the summation n equals 0 to infinity of negative 1 to the n. 1 over 2n plus 1, that's still a constant. Now we have the integral, x to the ninth times x to the 2n plus 1, that's x to the, you can add the exponents, so that becomes 2n plus 10 dx. Okay. Questions on that part thus far? So notice in terms of what we're doing, we get negative 1 to the n, 1 over 2n plus 1, and then we have, this is the antiderivative of that, will go 2n, you got to add 1, so that becomes 2n plus 11 all over 2n plus 11. And then plus some constant c sitting outside of there. So this whole integral, if we wanted to write a solution up, we get the sum n equals 0 to infinity. We have a negative 1 to the nth power. We have an x to the 2n plus 1, or 2n plus 11, my apologies. And then you have a 2n plus 1 and a 2n plus 11. And then all this, you just take plus some constant c. And you're done. And as long as your x values lie within the region negative 1 to 1, you're actually going to have an exact answer this way, right? If you had a definite integral you're trying to deal with. But so it gives us a nice solution, and if you were trying to do that another way, you'd probably still be working that problem. That's the beauty on power series. That's what we're trying to do, is cut down our time in order to calculate these things. And even with the power series, we can start to approximate those things really well too. So the other one, hopefully we do have written down, natural log of 1 minus x, and we'll finish with this one. So recall that that is negative, the summation, and then I think we'll use the n equals 0 to infinity. So it goes, I believe, x to the n plus 1 all over n plus 1, something like that. And so now in this case we have this thing equals x cubed times negative summation n equals 0 to infinity x to the n plus 1 all over n plus 1. You can try integration by parts and see with that. Once again, you'll have to use partial fractions and try and solve that. I think a much easier integral would be, well, we can first bring the x cubed on in. So we get negative summation n equals 0 to infinity. We'll have the 1 over n plus 1. We'll pull that out there, and we'll have x cubed, x to the n plus 1, and then a dx, right? And so from there, what happens? Well, you can pull the integral inside next to the x's because all the rest are constants. So this 1 over n plus 1 is a constant. It's not what we're taking our antiderivative of. We're taking our antiderivative of x to the n. Well, if we go 3 plus n plus 1, that's x to the n plus 4. And then you have a dx. And so all of this makes negative summation n equals 0 to infinity. You have a 1 over n plus 1, and then we have x to the n plus 5, when we add 4 and 1 makes 5, and then an n plus 5, and then plus some constant c once again. Okay, so at the end of the day, we have a negative summation n equals 0 to infinity, x to the n plus 5 now, over n plus 1, n plus 5, and then plus some constant c. And that's it. So hopefully that makes sense in terms of what's going on with all of these integrals, and you can see how those things work. And I hope all goes well with the upcoming homeworks. I hope you have a good one.